Okay, so our next topic would be about mirrors and how is image formed using mirrors and then using spherical mirrors. Okay, so let's start. Okay, a mirror is a highly polished surface which can produce images by the regular reflection of light. As we have discussed before, it follows the law of reflection wherein the angle of incidence is equivalent to the angle of reflection. And plane mirror produces images which are always of the same size as the object they reflect. Images appear to be as far behind the mirror as the object is in front. So the distance of the image and the distance of the object using plane mirror, they are the same. And then it's also producing a laterally inverse image. What do we mean by laterally inverse image? Now, do you observe this one, the term ambulance? If you are going to look at this term in a mirror, you will be able to read this as ambulance. So that is being laterally reversed. And also, if you're looking at the mirror and then you try to raise your right hand, it's like the image is raising its left hand. So that is laterally reversed image. So here is the formation for a plane mirror. So the light will reflect off the mirror according to the law of reflection. So as you can see here, the image is in the location where all reflected light rays will intersect. So you try to extend those light rays and then the image is appearing at the back of the mirror. We have two types of images. We have real image and virtual image. When we say real image, these are formed by actual rays. Maybe later I can show you a video on or a video of a real image. It's formed by actual rays. It can be projected on a screen and it's always inverted. Okay? And virtual image is formed by apparent rays of light, not the actual rays of light, but the extension of the rays of light, and cannot be projected on a screen, and it's always upright or erect. So if we are going to look at the different parts of the spherical mirror, we have this C, the center of the curvature, R, the radius of the curvature, F, the focal point, and the distance F here is the focal length, and then A is the vertex. And then the line here is the principal axis. The line here is the principal axis. We have two types of spherical mirror. We have concave mirror. If you have a spoon and then the spoon is toward you, yung curve niya ay papunta sa'yo, the reflective surface is curved inward, that is a concave mirror. It's also known as a converging mirror because it converges the rays coming or the rays bouncing off the concave mirror. Okay, again, it will converge. So you have here concave mirror, and then when you have a spoon again, and then the back of the spoon is facing you, that is a convex mirror. Now, there are two ways to identify where the image will be located. We have ray diagramming, and we can also use the mirror equation. If we will use the ray diagrams, we will follow the following rays. Ray 1, you have to draw this one. The incident ray parallel to the principal axis and is reflected through the real focus. Okay, maybe I'll show you a demonstration later. Number 2, ray passing through F and is reflected to the principal axis. And then 3, ray passing through C will strike at the mirror at right angle and will be reflected along its own path. Take a look at this. So we have here ray 1. Let's take a look at this animation. We have ray 1. This is ray 1. Parallel to the principal axis and then passing through F. And then ray 2 here. Passing through F and then parallel to the principal axis. And then you can see here that if you have here the intersection, this will be the tip of the image because we have started from this point. So you can see now here, or you can now observe that the image is smaller than the object. It's located between C and F, and then it's inverted. Okay, therefore, it's a real image. An indication that it's a real image is if the image is inverted. Okay, so that is one example. Let's take a look at this one. So you have here many rays drawn from the yellow bulb. Okay, 1, 2, and then you have here C. Passing through C. So ray 3 was used at this point, wherein ray 3 is at this one. So it passes through C. Let's wait for this. This is ray 3. So it was here reflected and then it bounces here. Okay, what if this time we have here the image is actually in between the vertex and the focal point? So how was it drawn? So looking at this, we have again ray 1 still parallel. Look, this one is still parallel here, and then it passes through F, and then the next one, it passes through F, and then it was reflected back parallel also here. But you can see here that we can now extend the rays. And the rays were extended there, and then the image is located here. So that image is actually virtual. So it's erect or upright, then it's larger than the image, and it's a virtual image. That will happen if, for example, you have a spoon. You move the spoon far from you, and then you can see an inverted image of you. But if you try to move closer, you will see a magnified image. So this image is magnified. Okay, it's located at the back of the mirror, and also it's upright, therefore it's a virtual image. Okay, now what I want you to do is I want you to try tracing the rays using this. So if the object is located at point C, the image is expected to be a real image, and also at point C. If the object is in between C and F, the image is expected to be magnified, and also it's beyond C and it's inverted, therefore it's real. If the object is located exactly at the focal point, no image is formed, so you will see no image. But if the object is placed between the vertex and the focal point, we are expecting that the image will be virtual and it's magnified. That's for concave mirror. Now let's take a look at the convex mirror. For convex mirror, the reflecting surface is curved outward. So as I have mentioned, at the back of the spoon, or the back of the spoon is facing you, that is convex mirror. It's known as diverging mirror because the rays are being diverged, or kumakalat yung rays niya if it hits a convex mirror, unlike in a concave mirror wherein it converges. So you have ray 1 from the top of the object parallel to the principal axis is reflected from the surface of the mirror and diverge, passing through the virtual F. The virtual F is located on the other side of the mirror. And then next, it's reflected back along the same line, is made to appear to pass through C. Let's take a look at this. Okay, for this one, only two rays are also used, just like in the concave mirror, wherein we can just use the ray parallel to the principal axis and then passing through F, and then a ray passing through F, then parallel to reflected back parallel to the principal axis. But this time you can see here, let's complete it. We have here the ray 1 and it's parallel to the principal axis, but it's diverged. But you have to make sure that the extension here should pass through F. If you're going to extend this line, it should also pass through F. But since it's diverged, so you can see here, it will be reflected back parallel to the principal axis. And then if you draw the extension, this intersection is where the image is located, or the tip of the image is located. Okay? So again, ray 1 would be parallel to the principal axis and then diverge, but the extension should pass through F. And then ray 2, the extension here should pass through F, but at this point, it will be reflected. And you have to extend the red one so that you can see where the image is located. Now, if we are going to describe it, the image is smaller than the object and it's erect, upright. So this one is a virtual image. So that's how we use ray diagram for spherical mirrors. So these are other drawings or other illustrations wherein you can see here that all the images are smaller than the object and it's upright and it's always virtual for the case of convex mirror. Okay, another way of identifying where the image is located is to use the mirror equation. We have 1 over dO plus 1 over di equals 1 over f, wherein f is equivalent to r divided by 2. dO is the distance of the object from the mirror, di is where the image is located, f is the focal length, and then r is the radius of curvature. Now, there are sign conventions aside from that. The next equation that we have would be the lateral magnification for us to be able to know if it will be magnified or it will be smaller. M equals hi, or height of the image, divided by height of the object is equal to the negative distance of the image divided by the distance of the object. Okay, but we have to use sign conventions for accuracy. We have to see the distance of the object is always positive whether it's convex or concave mirror. The distance of the image could either be positive or negative. Positive if the image is in the reflecting side of the mirror. So it will also produce real image. If the distance is negative, that means it's behind the mirror or at the back of the mirror. So that is virtual image. The height of the object is always positive. But the height of the image, if it's positive, that means it's upright. So that is virtual. If the height of the image is negative, that means it's inverted. Therefore, it's a real image. For the focal length, for concave mirror, we always use positive focal length. But for convex mirror, we will use negative focal length. Okay? So you have to remember those sign conventions. Okay, we will solve this problem. Okay, so let's try to solve sample problems in mirrors. We have number 1. A 7 centimeter candle is placed 20 centimeters from a concave mirror whose radius of curvature is 30.0 centimeters. Solve for the position of the image and the size of the image. So we are looking for the DI and also the HI. We're given here the height of the object and then the distance of the object. And R is equivalent to 30.0 centimeters. So let's start. Okay, now let us recall our equation. We have 1 over dO plus 1 over di is equivalent to 1 over f. But what we are looking for is the distance of the image. So let's just have 1 over the di is equivalent to 1 over f. Then place it on the other side, minus 1 over the distance of the object. So we can now substitute 1 over di is equivalent to 1 over the focal length would be half of the radius of curvature because we have f is equivalent to r divided by 2. So half of this one is 15 centimeters. 1 over 15. Then you have here minus 1 over the distance of the object is 20 centimeters. Take note also that you don't have to convert units as long as the units are consistent. For example, in this problem, we have 20 centimeters, 30 centimeters, and then the height is also 7 centimeters. So our final answer would also be in centimeter. So calculating this one, 1 over 15 minus 1 over 20. Okay, so use your calculator, get the reciprocal of 1 divided by 15 minus 1 over 20. You can use all the decimals and then you just get the reciprocal so that you will have an answer of di. Okay, you can now get an answer of di is equivalent to 60 centimeters. Again, if you're going to use the whole decimal, or if you're going to use all the decimals found in your calculator. So again, 1 divided by 15 minus 1 divided by 20, then you get the reciprocal of that. So that is 0.0167 and so on. Then getting its reciprocal, you will have distance of the image equivalent to 60 centimeters. So this one is positive. That means the image is located on the same side as the object. So this image is a real image. Okay, so you have to take note that it's also a real image. Then next is to solve for the size of the image. We now have an equation wherein magnification is equal to negative di over do, but that is also equal to positive height of the image divided by height of the object. So we can use this expression because we don't have the magnification, so we can use this since we have the di, do, and then also the h or the height of the object. So height of the image is just as simple as negative, we have di ho divided by distance of the object. So in our given, or in our solution before, we have negative 60 as the distance of the image. The height of the object is 7 centimeters, and then the distance of the object is 20 cm. So our answer here for the height of the object, let's check. Okay, the height of the object is equivalent to 21 centimeters. So the answer here is negative. The height is negative 21 centimeters. So when we say that the height is negative, that means that the image is inverted. So again, as I have mentioned, since the image is inverted and is also found on the same side as the object, therefore the image is a real image. It's produced by actual rays of light. Okay? So let's now solve the next item. Determine the location of the image and the magnification for an object 5 meters from the convex rear view mirror if the radius of curvature is 0.4. So again, we are looking for the distance of the image. Since we are looking for the distance of the image, we will be using same equation we have. Okay, we'll be using same equation. We have 1 over di plus 1 over do is equivalent to 1 over f. Therefore, our 1 over di is just 1 over f minus 1 over do. Then we get the reciprocal of this so that we can get the distance of the image. Now, the radius of curvature here is 0.4. Therefore, the focal length is half of that. That's 0.2. Okay, so we have 1 over di equals 1 over f minus 1 over do as derived from the equation. But take note that this one is a convex mirror. So if we are referring to a convex mirror, therefore the focal length is equal to negative, or it should have negative sign. The focal length here is negative 0.2. Okay, so let's solve. 1 over di is equivalent to 1 over the focal length is negative 0.2 minus the distance of the image, or the distance of the object is always positive, so that's 5 meters. So that will be 1 divided by negative 0.2 minus 1 divided by 5. So let's check. Okay, the answer here, 1 over di is equivalent to negative 5.2 meters. However, we have to get the reciprocal so that we can get the distance of the image. So the distance of the image is equivalent to negative 0.19 meters. Okay? So the distance of the image is negative. That means that the image is found at the back of the mirror. That's why in a rear view mirror, you can see there the image sa parang nasa loob siya ng mirror. Okay? Now, solving for m, we have negative di over do. That's the magnification. Okay, so you have here negative. Then the distance of the image that we got is negative 0.19 meters. Then we have here the distance of the object is 5 meters. So our answer for M would be 0.038. 0.038, or we can have 0.04. But this time it has no unit because you have meter here. So we can just cancel the unit meters. So magnification is unitless. So you can see here that the magnification is smaller than 1. Therefore, the image is not magnified, but it will be smaller than the object. Okay, let's have the next problem. A 1.5 centimeter high diamond ring is placed 20 centimeters from the concave mirror, whose radius of curvature is 30.0 centimeters. Determine the position of the image. So again, we are looking for the distance of the image, and then we look for the height of the image. So same method. 1 over di equals 1 over f minus 1 over do. So the focal length, since the radius of curvature is 30, our focal length is 15 centimeters, and it's positive since we are dealing with concave mirror. So we have 1 over 15 centimeters minus the distance of the object is 20, so 1 over 20. Now our answer here, 1 divided by 15, minus 1 divided by 20, you have 0.016 and so on. Getting the reciprocal of that, you will have the distance of the image to be at 60 centimeters. So we were able to answer the position of the image, and now let's look for the size of the image, or the height of the image. And recall that the formula would be, we have height of the image over height of the object equals negative di, or distance of the image, divided by distance of the object. So let's look for height of the image. It will just be negative di ho and then do. Substituting the given, we have the distance of the image, it's 20 centimeters. The distance of the image that we got is 60. And then the height of the object is 1.5 centimeters. So again, units are consistent, so no need to convert. Then the distance of the object is 20. Sixty times 1.5 divided by 20. Okay, our answer would be height of the image is equivalent to negative 4.5 centimeters. Now you have here the height of the image is negative 4.5 centimeters, so that means that the image is inverted. If it's inverted, therefore you have a real image. Okay? So that will be the end of our discussion on mirrors. Next meeting, we will be having a discussion on lenses. And then we'll have a seat work.